Okay, this problem is where you're trying to find the change in energy for each metal that produced the color of light that you saw. So this is the post-lab question number 3 on page 4 of the handout. And so the first thing that you're going to have to do is make sure you've done problem 2, which is convert the wavelengths from nanometers to meters. So I'm just going to do the sample for calcium. And so you would have to flip back through your paper and go to the second page, and I believe calcium was the, let's see, I can't remember. Oh, maybe I better do one that I know. Let me do the red one. The red one was the one that lithium made. And so red, if you look at the thing, red has a wavelength, and so the symbol for wavelength is lambda, and so the symbol for red, the representative wavelength, is 650 nanometers. So what you're going to have to do is change nanometers to meters. And so you would go 650 nanometers, and then you just draw a picket fence, and you're going to say that in 1 meter there's 1 e to the 9th power nanometers. Nanometers are way smaller. So you need a lot more of them to make up 1 meter. So anyway, let's see here. So 650 divided by 1 e to the 9th, and that equals 6.5 e to the minus 7. So the wavelength, it's a very small one, is 6.5 e to the negative 7th meters. That's for red light. So I'm doing this one for red light, which is the lithium metal, I believe is what you will find. Okay, anyway, so then once you get that, you can use this equation here, that the change in energy is going to be equal to Planck's constant times the speed of light divided by the wavelength. Okay, so the change in energy, this is what we're trying to calculate, is equal to Planck's constant, which is 6.62 e to the minus 34 joules times seconds times the speed of light. And I know it gives it to you on the paper like 2.99, something like that, e to the 8th, but I'm just going to round it to 3.0 e to the 8 meters per second, and I'm going to divide that by the wavelength that we just calculated above, which is 6.5 e to the negative 7th meters. And that's the reason why we had to change nanometers to meters, is because we're using the speed of light with meters and we need the units to cancel. And then this seconds will cancel, and what we're left with is an energy unit of joules. And so if I do the math here, if I take Planck's constant 6.62 to the negative 34 times 3 to the 8th power, 3 divided by 6.5 e to the negative 7th, I get around 3.1 e to the minus 19th. So the change is equal to 3.1 e to the negative 19th joules. Now what that represents is if you have an electron, let's say normally, let's just pretend one's in the first energy level, and then if you remember, then we have 1s2, this would be like 1s, 1s, I guess there's only one there. Then up here we have the 2s, and then we have the 2p. Well, an electron can be excited if you like put fire underneath it, and it can jump up to a higher energy level. But then when that electron falls back down to a lower energy level, it gives off energy, and the change of energy that you just found right here, or I just found, I guess, represents an electron falling from a higher energy level to a lower energy level. And if that energy is just right, it will produce the color of red light. Okay, so that's how to do a problem like that.